That's when we ran into trouble before.
Oh, really?
But we can try it.
Yeah, because now we can see that it's
Okay, hi everybody online. Can you hear us now?
Okay, we've got some okays online. Okay, thank you very much. So I'm going to introduce our first talk, and hopefully we will not hear this in echo mode. So that will be given on HawkSat by Adam Bourassa. Please take it away.
Okay, great. Yeah, thanks, Kaley. Thanks, everybody, for sticking through our technical difficulties here. My name is Adam Bourassa. I'm from the University of Saskatchewan, and I'm going to talk about some specific elements today of the Canadian HAWK mission. This is a satellite mission that is fully funded here in Canada. It's being developed by the Canadian Space Agency in collaboration with a large group of academics, as well as ECCC and NRC. And specifically today, I'm going to tell you about two of the three pieces of instrumentation that make up HAWK, and these are the limb profiling elements. Okay, so HAWK, which stands for the High Altitude Aerosol Water Vapor and Cloud Satellite Mission, is a Canadian satellite mission, but it's also a Canadian contribution to a much bigger multi-satellite mission that's called the Atmosphere Observing System, and that's led by NASA. And the Atmosphere Observing System is actually one of the missions that was motivated by the Decadal Survey in 2018. And here you can see a figure that comes from the Decadal Survey. Decadal Survey identified these 5 priority areas of measurement for Earth observation for the coming future. And very early on in the process, NASA realized that the needs for cloud convection and precipitation, as well as the needs for aerosols, were met by highly complementary instrumentation. You need the same type of instrumentation, the same type of coverage to answer the questions about clouds and precipitation as you do for aerosols. So they started to develop one atmosphere observing system mission that would cover the needs for clouds and aerosols together, and that's AOS. And AOS is really then designed to measure the vertical structure of aerosol and cloud, as well as ice and water vapor, to observe the interactions of aerosol and cloud, and to try and link cloud and aerosol properties to the radiation and climate feedbacks. So HAWK is a part of this much bigger mission. And this much bigger mission, AOS, is a collaboration of 5 countries led by NASA, flying 6 satellites in 2 orbits. And you can see these 2 orbits depicted in the 2 diagrams here. On the left-hand side is an inclined orbit, and this is referred to as AOS Storm. And on the right-hand side is a polar orbit, and this is referred to as AOS Sky. The inclined elements will launch a little bit earlier. Right now, the plan is for 2029. And then the polar elements will launch 1 or 2 years later, around 2030 or maybe 2031 right now, depending on some schedules that are out there. And the Canadian elements, HAWK, are part of the polar part of the mission. And so you can see here the Canadian flag is beside this satellite, which is named HawkSat, which has 2 instruments on it, the Aerosol Limb Imager and Spatial Heterodyne Observations of Water. And another Canadian element here with this Canadian flag on the NASA Polar Orbiting Spacecraft, which is labeled here as the Far Infrared Imaging Radiometer, and that instrument is called TICFIRE. Okay, so here's a picture of just those 2 satellites flying here together. Here's the AOS polar satellite with the TICFIRE Far Infrared Imager, imaging cloud tops and the ground here in the far infrared. And the Canadian satellite, which we call HawkSat, has the 2 limb profiling elements on it, ALI and SHOW. And the 2 satellites, are flying in coordinated orbits so that the tangent point of the limb measurement is aligned with the nadir point of TICFIRE and the other AOS Sky instruments, so that we get this coordinated, coincident view of the same air mass. So yeah, like I said, 2 instruments here that are looking at the limb profile to measure the vertical profile of aerosol by ALI and of water vapor. by show. Okay, and so the science that we want to do with HAWK was always designed to be very complementary to the science of the broader AOS mission. HAWK is focused on the high altitude and high latitude, cold and dry regions of the atmosphere. So really the mid and upper troposphere and the stratosphere, looking at ice clouds, looking at aerosols above the clouds, specifically stratospheric aerosol, and looking at the changing water vapor near the tropopause, which is a very challenging measurement to make because of the strong gradients that are there. And there's some really critical physics that happens here. Like I said, we want to look at ice clouds, specifically the formation and distribution of ice clouds, and the role of water vapor and aerosol in these cloud processes. Wildfire smoke is another thing that we're targeting with HAWK, especially with ALI. And you can see this little schematic that we developed on the right-hand side that tries to sort of showcase some of the science and the interactions here. So you have tick fire on a nadir viewing satellite at the top, looking down with the gray field of view at the cloud top. And then you have ALI and show on the right-hand side here, looking in the limb, measuring the profiles of aerosols and the profile of water vapor. And it's this region right here in the UTLS where ice clouds, water vapor, and aerosols interact, where the mission will really be the strongest. Okay, so I want to just spin through a little bit of the products that we intend to measure and how we intend to measure them. So here we have the aerosol limb imager, and that's what I'm going to focus on first. It is designed to measure aerosol extinction, which is a standard measurement in the limb, but also will measure the effective radius or some metric of the particle size of the aerosol size distribution and the cloud top. And we intend to do this from the mid-troposphere, around 5 kilometers, up through the stratospheric aerosol layer into the middle stratosphere, around 35 kilometers. And we're going to try to do this with quite good vertical resolution, certainly sub-kilometer, and measurements along the satellite track every 10 to 15 kilometers. So this is what that measurement concept looks like. So Ali is here on the satellite looking out at the limb with a two-dimensional field of view, measuring the scattered sunlight from the atmosphere. So it's not looking at the sun the way some limb occultation measurements work. This is really just looking at the sunlit atmosphere and measuring the scattered sunlight. So you can imagine Ali just basically taking pictures of the side view of the atmosphere. And as the satellite flies along its orbit, these pictures have a selected wavelength and a selected polarization state. And that wavelength switches between 610 nanometers and 1560 nanometers and cycles between polarization states. And then the polarization information and the spectral information is all collapsed together and used in a single retrieval of aerosol extinction and aerosol particle size. So you can get profiles as well as cross-track information for context. And I think this figure actually shows you one of the reasons why we need this type of measurement quite badly. So a couple of years ago, there was quite a large volcanic eruption in Tonga called Hunga. And you can see here the suite of currently existing instruments that are able to measure aerosol above cloud in the stratosphere. One of them is SAGE, which measures by solar occultation. One of them is the Canadian OSIRIS instrument. And then I have three other lines on here, which are three different level 2 retrievals from the same NASA measurement set from the OMPS satellite. And you can see that in a couple of different latitude bands, the time series of aerosol optical depth has, quite a bit of variability. This is due to wildfire events and smaller volcanic eruptions, but the data sets hang together pretty well until we have a bigger volcanic eruption or a wildfire event. Tonga is here, this big one. And you can see that the situation really becomes quite a disaster at that point, where none of the data sets really agree to within basically an order of magnitude. Even retrievals running on the same radiance measurements disagree wildly with each other. And the reason for this is because of the lack of aerosol particle size information. Aerosol particle size has big uncertainties, and those uncertainties fold into the retrieval algorithms and mean you get big biases in retrieved extinction. And extinction is really the climate parameter that we're after in the end. So we need a measurement set that will give us not only extinction, but particle size at the same time, and try to collapse all of this uncertainty. Another challenge we have with the current data sets is that it's very hard to discriminate aerosol plumes from thin cirrus clouds. You can see an example here where we found aerosol measurements from OMPS and calypso measurements of cloud in a very close coincident. Basically, the two satellites' orbit tracks align every once in a while, and you can plot those two parameters together as a function of latitude here and altitude. And you can see all the clouds measured by the calypso LiDAR in blue, and you can see the retrieved aerosol extinction field from the OMPS measurement in red. And there's a lot of really sort of interesting, what looks like interactions between the aerosols and the clouds, the aerosols likely stimulating cloud formation. But it's really hard to trust the aerosol product in the cloud region because you can't discriminate the scattering from the cloud well from the scattering from the aerosol. Okay, and one of the ways that we've designed ALI to deal with this is with the polarization information. So with an enhanced spectral range and with dual polarization information, we hope to be able to retrieve aerosol particle size and to discriminate well between aerosol and cloud. And so here's a simulation of ALI performance on modeled aerosol and cloud fields. So as a function of latitude and as a function of altitude, we've taken high resolution model field, simulated aerosol measurements, retrieved with the ALI algorithm. We can retrieve aerosol particle size, extinction, and detect the cloud top with quite good vertical resolution. Okay, the second element I want to talk about is the water vapor measurement. This comes from the Spatial Heterodyne Observations of Water instrument, or SHOW. SHOW is also designed to measure in the limb, the vertical profile, and to do it with quite high vertical resolution, sub-kilometer, and good precision, less than 1 ppm, even up into the stratosphere where it's quite dry. This uses a similar concept to ALI, where we're looking in the limb, essentially taking pictures of the limb, but the light is put through a spatial heterodyne spectrometer, which gives you an altitude by spectral image for each one of these observations. And those can be used together with a retrieval algorithm to get you water vapor profiles. The difference here is that the spectral range is very tiny. The spectral range is only 4 nanometers. The spatial heterodyne interferometer can resolve it. The water vapor absorption lines in the 1.36 micron band quite well, and that's the information that's used to retrieve the water vapor profile. I won't get into too many details about SHOW, but SHOW is really a one-trick pony designed to only measure water vapor, but to do it extremely well. So the vertical resolution is sub-kilometer, especially at the lowest altitudes. This is something that's really never been done before. Other measurements are way out in the 2, 3, 4 kilometer vertical resolution. And with accuracies, like I said, at the 1 ppm level. Okay, and just before I wrap up here, I want to show just a little simulation about SHOW performance that was done by Yi Wong's group at McGill. This paper came out in JGR about a year ago, where they took high-resolution model fields of a convective water vapor event using the GEM model, and using the averaging kernels from current generation of sensors from MLS and from AIRS, as well as what we plan to get from SHOW. The paper was able to show that really it's only the SHOW instrument that's able to resolve this convective water vapor plume. So we're looking forward to being able to produce data sets that look something like this here in the bottom left corner. Okay, and we will hear more about tick fire later in this session, so I'll just tell you a little bit about where we're going from here to try and get to space in 2031. There are a number of technology demonstration studies and development studies that are underway right now with Canadian industry. Light Machinery and ABB are furthering the development of the spatial heterodyne spectrometer. Honeywell is working on the optical design for the ALI instrument. At USask and also at UQAM in Montreal, we are developing the plan for the data processing centers. We have completed one flight on the NASA ER2 with ALI and SHOW last year or so ago, and you can hear a little bit more about that in the PONEX session on Wednesday, as well as the planning to fly ALI and FEAR on PONEX in 2025. And the science team is also currently being developed. There's some CSA funding and an NSERC Alliance grant that's held at McGill, which is meant to develop that science team. And we're also planning an NSERC Create program proposal to fund HQP to work on HAWK. So thanks very much.
Thanks very much, Adam. Are there questions in the audience?
Thanks for the presentation, Adam. Quick question is, are there complementary observations below the 5-kilometer altitude that, for example, about water vapor or aerosols?
Yeah, and I think that's part of the strength of being part of this much bigger mission, is that the bigger mission will also fly LiDAR, will also fly multiple radars and polarimeter. So the troposphere and the lower troposphere is covered quite well by the active sensors and the nadir imaging sensors.
Anyone else? Okay, I'm going to scan anyone online. Were there any questions? Okay, so we will move over to our next presenter. And so I'm going to invite Emily Tracy to come up to give her presentation, which will be looking at simulated measurements of aerosols from MPL-CAN and Ali. It's that one.
Oh, there it is.
Is there a clicker? Nice.
Yes, right there. Green button.
So hi everyone, my name is Emily Tracy and I'm a master's student at Western University. So my project is investigating how Ali, the aerosol limb imager that Adam was just talking about on HawkSat, can be used along with a ground-based LiDAR network called MPL-CAN to help improve our understanding of aerosol. So what I've found and what I'll show you today is how MPL-CAN can possibly extend the vertical coverage of Ali aerosol measurements all the way to the ground. MPL-CAN may be able to validate Ali measurements at altitudes where both instruments can measure, which is from about 5 to 10 kilometers. And then the last thing that I'll show you is simulated MPL and Ali measurements of a wildfire smoke event, which means that they could possibly be used together to track a wildfire smoke event across the country. So to start off, what are the LiDARs that we're working with? These are micropulse LiDARs, which are elastic backscatter LiDARs, which means that they transmit and receive light at the same wavelength, and this is 532 nanometers. They're also dual polarized, which allows for total volume depolarization measurements, and this is really useful to help us distinguish between aerosol and clouds. And MPL-CAN is the Canadian Micropulse LiDAR Network. So this is a network of 7 mini MPLs across Canada, and on the left here is a picture of what the mini MPLs look like. And this is a smaller branch that's a part of a larger LiDAR network run by NASA called MPL-NET. And if you're interested in learning more about MPL-CAN, you can attend my colleague Victoria's talk today at 4 p.m. So here's an example of what MPLs measure. So the top plot here is normalized relative backscatter. So these were taken from our London, Ontario MPL in October of 2024. And the backscatter plot on the top, this just tells us the amount of radiation that's scattered back to the LiDAR receiver. And around 10 kilometers, you see a high signal where there's a cirrus cloud. And then the bottom plot is the volume depolarization. So you can see really high depolarization where the cirrus cloud is, which is what tells us that it's ice. And then you also see signal closer to the ground in the planetary boundary layer. And we can tell that those are aerosols because they have lower depolarization. So the challenge with comparing MPL and Ali measurements is that they don't measure exactly the same thing. So what MPL measures is photon counts, but then from that, we can derive attenuated backscatter shown in this equation here. So this is a function of both backscatter and extinction, where backscatter is the amount of radiation scattered at 180 degrees, and extinction is the amount of radiation scattered in all directions and lost through absorption. So with elastic LiDARs, we can't separate the extinction and backscatter without assuming something called the LiDAR ratio. And this is just the ratio between extinction and backscatter, and it's been calculated by in literature for different types of aerosols, but typically has pretty large uncertainties associated with it. LE, on the other hand, what it actually measures is limb scattered radiance from the sun, but then from that we can retrieve aerosol extinction and aerosol particle size. So to compare the two instruments, I am converting the LE products into backscatter, and there's two different ways I can do this. The first way is simply to just assume a LiDAR ratio and then use the LE retrieved extinction and this simple equation here to get the backscatter. And the only problem with this is, like I said, the LiDAR can sometimes have large uncertainties, but this is what is typically done because typically we don't have particle size information, but it's something really interesting that LE can provide, which allows me to use the second method, which is to use the size distribution, mean theory, and then assume an index of refraction to calculate the backscatter coefficient. And I do this by calculating the differential scattering cross-section by integrating over the backscattering efficiency and the size distribution. And the challenge with both of these methods is that we do have to know what the aerosols are up there to be able to assume the LiDAR ratio and the index of refraction, so this can add a little bit more uncertainty. So to test these methods, I'm looking at two different cases. The first is stratospheric aerosols using the Global Space-Based Stratospheric Aerosol Climatology, or GLOSAC, and this is kind of what LE is really optimized to measure. So I input this model into the LE simulator developed at the University of Saskatchewan, and this produces a simulated measurement, and then from that I can perform a retrieval, which you see here. So in blue is the retrieve profile, and then in red is the true profile, and you can see that it performs really well. And then I can use these products in the two methods that I described earlier to convert it into a backscatter. So in teal, you see the first method using the LiDAR ratio, and then in yellow is the second method using particle size, and in red is the true profile. And I use the assumed LiDAR ratio and index of refraction shown here, which I found in literature for 75% sulfuric acid and 25% water, which is typical in the stratosphere. And the uncertainties on these come from the covariance matrix in the retrievals, as well as the uncertainty on the assumptions. So you can see that both methods agree with the true profile within uncertainty, but the LiDAR ratio method has a much bigger uncertainty just because of that large uncertainty on the LiDAR ratio. So then next, I can input the same GLOSAC model into an MPL simulator, and that produces an attenuated backscatter. So I co-added the MPL measurements to a vertical resolution of 840 meters to kind of be closer to that of LE, and I averaged over an hour of measurements to reduce the noise. So here I'm plotting the MPL and the LE measurements, and what I'm actually plotting is the attenuated scattering ratio. So this is just the attenuated backscatter normalized by the molecular attenuated backscatter just to bring out that aerosol signal. So, and this attenuated scattering ratio can be below 1 because it's attenuated backscatter, not just backscatter, and there's those high aerosols below 5 kilometers that attenuate the signal. So what we can see is that below 5 kilometers, only MPL is able to measure. From about 5 to 10 kilometers, both instruments can measure and relatively agree. And then above 10 kilometers, the noise in the MPL becomes far too large for reliable measurement. But that's exactly what we would expect. MPL is not designed to measure these low aerosol loads at high altitudes like this. And this was also simulated during the day when there's a lot more solar background, but we have to do that because that's the only time that LE can measure. So then the second case that I'm looking at is something that MPL is designed to measure, which is wildfire smoke. And that's something that we're really interested in with MPL CAN. So you may remember from June of 2023 when really heavy wildfire smoke covered a lot of Eastern North America. So these are some pretty famous pictures from New York, Toronto, and Washington. And we also observed this smoke layer in London, Ontario, using our MPL at Western University. So this measurement was taken on June 8th of 2023. And I chose this one because there's a smoke layer from about 8 to 10 kilometers that you can see, which is in the range that both MPL and LE can measure. So you can see the top plot again is backscatter, the bottom plot is depolarization ratio, and you can see that it has a much lower depolarization ratio than that cirrus cloud that I showed you earlier. So this is how we know it's smoke. So then I'm simulating this layer using typical optical properties of smoke found in literature, and then I adjusted the number density to match this relative backscatter. And so I inputted that model of smoke into the ALI simulator, performed a retrieval. This time, we were not able to retrieve particle size yet. It's a difficult retrieval just because of the absorptive properties of smoke, so we're only able to get extinction, but it can do that very well. So then from that extinction, I can assume a LiDAR ratio and get backscatter to compare to an MPL profile. So that is the plot that you see on the right. And you can see that once again, below 5 kilometers, only MPL is able to measure. And then from 5 to 10, both instruments are able to pick out that wildfire smoke layer. And then above 10 kilometers, the noise in the MPL dominates. So in conclusion, I've found that MPL can be useful to extend the vertical coverage of ALI to the ground, but other more powerful LiDARs will be more useful to validate ALI's stratospheric aerosol measurements. And then in the future, it'd be interesting to try to improve the ALI retrievals for these smoke cases with high extinction and absorption to be able to also retrieve particle size. And it'd also be interesting to look at ALI and MPL measurements of other aerosol types like dust and volcanic ash. And some challenges with that are that both of those have relatively large particle sizes, and then they can also have absorption. So finally, I'd just like to thank my supervisor, Bob Sika, my colleagues at Western University, and then the collaborators on the Hawk ALI side, Landon, Adam, and Doug, for helping me out with this project.
Thanks very much, Emily, for a very nice talk. Any questions? Oh.
I just want to make one comment. Very nicely done.
Thank you.
Very good job. Your results, are those typical results, or are they all So my question was, the results that you showed, they look very, very good. Are they typical, or are all the results, or were these just ones that were selected because they were the good ones?
Yeah, so for the smoke case, there's a huge range of different index of refraction in literature that I found. So sometimes if it's really, really high, the retrieval does not perform well. So for this case it did, but yeah, not all of them perform well, but sometimes it does. Mm-hmm. Thanks.
Any other questions in the room? I'm going to go to Ian and back to Matt.
I echo Doug. It's a really nice talk. In the first case, in the comparison, if you don't mind showing that picture again, do you have a choose profile that has no aerosol in the lowermost layers, but the retrieval has some similarly aerosols? Yeah, like the left figure. Can you comment on that discrepancy there in the lowermost 5 kilometer?
Below 5, like on the left here?
Yes.
Yeah, so there are some aerosols below 5 kilometers. ALI's not able to retrieve below 5 kilometers. So I'm not sure why the actual retrieval doesn't show 0, to be honest, but I'm assuming it can't go directly to 0 that way. But it's not designed to measure below 5 kilometers, so we can't really trust those measurements.
Hi, yeah, great job. You mentioned that you were looking at daytime measurements because ALI only measures during the day. But just wondering, how much better are the MPL measurements if you measure at night? And so if you were to look at, rather than exact comparisons, but like more a monthly mean or something like that, would you get more extension of MPL into higher altitudes?
Yeah, it can go up to probably more like 15 kilometers, maybe even 20 if it's like not a lot of aerosols or clouds in the way. So it can go quite a bit higher at night.
Great, thanks.
Thank you very much. Let's join me in thanking Emily again for a lovely talk. And our next speaker is going to be online. So Jan, are you there and ready to go?
Yes, I'm there, and can you hear me?
Jan, I cannot hear him.
Oh, okay.
Can you hear me now?
Jan?
Yes, I'm talking. Can you hear me?
We can see you, but not hear you.
Okay, is it on your side?
So we've been asked for you to check if your microphone is on.
I will try another microphone. Can that work now? Can you hear me now? No?
Okay, Jan, give it a try, please.
Yeah, okay. Can you hear me now?
Nope. I see Jan talking, and I'm not hearing Jan.
Okay, I'm trying another microphone. Can you hear me? No, not yet. I've tried the 2 microphones for now. No. Okay. Yeah. I again the first microphone.
It's supposed to be the Scarlett speakers.
Yeah. I can. Yeah.
Okay, Jan, give it another try, please.
Yeah.
Oh,
My mic is working. Can you hear me?
try the other one. Nope, that doesn't help us, does it?
No, I'm trying again. And can you hear me now? I see my mic is working. No.
Okay, so luckily everyone can hear him online. We just can't hear him in Saskatoon.
Oh. Okay. I will
Jan,
wait.
can you yell louder so we can hear you many provinces over, please?
Can you hear me?
There we go.
No, I think you had the same issue this morning. So I don't know if you can try the solution. No, test 1 2 1 2.
Well, there's that window, which isn't really a helpful window.
Yeah, I can still hear you, but not.
And there's nothing else that's connected into our system. Again, our apologies, everyone online and in the room, for the technology fun we are having.
Oh. Yeah, test 1
Jan,
2 1
while
2.
we're at this,
Yeah.
do you want to try sharing your screen?
Yeah.
Because what I'm seeing is our screen, not yours.
I'm sharing my screen now.
Yeah.
Can you see it?
Okay.
Did that work?
Sorry, I'll be a minute. Someone's on their way home. Okay. Let's hope.
Yeah. Oh, yeah. Otherwise, you can share my, present my slides and I can talk. Yeah.
We've tried all the work tricks,
I can't
haven't we?
think of anything else to try, actually.
Yep.
Yeah, we have. So Jan, can you share your screen, please?
Yes. This is my screen. Can you see it? I'm going to present a mode, to a full screen. No.
Right now, we only see you. We do not see the screen.
Yeah, I'm sharing my screen. Yeah.
Yes. Yep.
No.
I hear something right here.
Can you hear me now?
Off here.
Let's see. Yeah, you.
I need to unmute my laptop as well.
Let's see.
Okay, so
Okay. Yeah.
that's pretty good.
Share share again my screen.
Jan, we can also share our screen. I think the problem is whether or not we can actually, the bigger problem is we can share your slides, but that doesn't necessarily come with your voice. And I
Yeah.
don't think you want me to give your talk.
No. Yeah. Do you have any solution?
More of threat than promise.
Yeah. Yeah. We'll try this. I will try with another browser. Maybe that's another solution. Can you hear me now? I can hear myself.
Is he able to share his slides?
No, it's not. Yeah, the biggest problem is he's speaking. We just can't get the connection.
Yeah. Can you hear me now? Yeah. Try different options, but still not working.
No.
I'm sharing my screen, but then not working. Yeah. Not seems to work. No. I don't know what I can do.
Okay, Jan and Atif, in the interest of not completely having everyone disappear into their phones and their email, can I propose to you that we will try and solve the technical problems, but we'd like to move someone who's in the room who we think we have the technology working for, move their talk up and get Anne to do their talk first? Is that
Yeah.
okay?
Yes.
Can you give me a thumbs up or a thumbs down, Jan? There was a thumbs up? Okay, great. Excellent. Okay, brilliant. So, stairs over here. T guy just showed up. Okay.
I'm just with the IT guys are here, so maybe we can.
Yes, once we make plans, then of course, I think we can get it. Okay, Jan.
Is the DI muted in the control room for me, Rob?
Hear me now?
Can you unmute the Zoom?
Jan, can you just start talking?
Yes. Yes.
Parfait.
Okay. And can you see my slides?
Can you do the Sharify or do you want us to do it?
And right now I'm sharing my screen. So if it's not working again, I prefer you share. Can you see it now?
We're not seeing anything, we're seeing you, but we also have the tech people.
Yeah, I don't mind if you share the screen for me. Yeah, if it's easier.
Tech people, could we make sure that we have the slide shared, please? Because right now we're just seeing the speaker.
He thinks he is.
He thinks he's sharing his slides. He
Yes.
knows he's sharing his slides. He pressed the share button.
And I see the thing on the top of the panel. Yeah, okay. No. Is it working on your side?
And
I'm ready to go.
yep, he's working on it. Presenter mode, Jan?
Yes, this one.
Yep. Okay,
Okay, now what do I do?
I think that's us.
Yeah.
Full screen this or something.
Yeah, there's a full screen that
Should be this little thingy in the corner that you can barely see.
Yeah.
Wow.
Okay, knocking on whatever this is made of. Our next speaker is Jan Blanchard, who's going to tell us about far infrared observations and preparations for AOS Hawk. Please, Jan, take it over.
Yeah, thank you very much for waiting. And yeah, next time I will go to the conference. It will be easier. So I will talk about lesson learned and insights from far infrared observation in the preparation of Hawk and AOS missions. So I'm Jan Blanchard, and I would like to thank the UQAM team and also the Canadian Space Agency for funding this work. Yeah. So the outline of my talk is first I will say a few words about thick fire and the missions. I will briefly present the far infrared observation database that we are using, and I will present some of the lessons learned and insights from this database. So 4 main points today. One is to show the importance of having an end-to-end simulator that's ready that help for the mission preparation and especially reliable. Also, it helps to do some early performance evaluation and also with the algorithm development. I will talk about the critical role of the calibration and validation strategy. And also I will finish with some fear observations that will help to deepen the mission objectives and enhance the scientific impact. So you have seen some of those components previously presented by Adam. So I won't go too much into details. So there is Hawk and AOS. And as you can see, TICFIRE is on board the AOS Sky satellite. So it's still under construction. But what I want to mention, it's really the great level of synergies that we can have into those different instruments. Few words about TICFIRE. So it's a spectral imaging radiometer that covers the thermal to far infrared on 8 bands with a GI/FOV of 2 kilometers or less. And we have two main interests. The first is the thin ice cloud properties, microphysical properties, and the processes. So the formation, the nucleation, the evolution, precipitation, and that will help to better understand the aerosol cloud water vapor interaction. The second topic is Earth radiation budget. And what's really new with TICFIRE is to bring the spectral information to do the cloud relative effects and the spectral radiation closure. So you have heard previously from Zipeng, that's what is done on board Earthcare. So it's really important to give strong constraint for the spectral signature for atmospheric and climate model. And why we are so interested in far infrared, it's because more than 50% of its energy leaks to space in the sphere, and it's only observed spectrally from satellites since last year. It's still at a large spatial resolution. And the sphere is highly sensitive to ice crystal size and phase. So you can see the two panels. The first is a refractive index, where you can see water, ice, and dust, the real part. And the single scattering albedo, well, it shows three different sizes, from 20 in blue to 100 in yellow. And we will use this spectral signature to retrieve cloud effective radius. It's also sensitive to cloud optical depth, temperature, and humidity with some profiling capabilities. And last, we think that could improve the forecast in convective and synoptic storm activities using data assimilation. So to present you the database we use, there are several campaigns where we use those far infrared data. Some ground-based, where we have some IRE and FEAR-1, which is a prototype of TICFIRE that was settled at Eureka 10 years ago. IRE during the LAJOLA during the EPCAPE campaign 2023. And recently we had the WAFERS campaign, so at the beginning of this year, with FINES, FIRMOS, and IRE. So it's a 3 spectrometer at 0.5 to 1 wave number, and it's a very important data set for us. We use also airborne observation from FIR1 and FIR2 during WAFERS, so we can see the Convenors airplane, and recently the pre-fire satellite observation. And we also use the TICFIRE end-to-end simulator at different altitude, and we need some input about atmospheric and surface conditions. So we use weather balloons, LiDAR, radar, and also some GEM simulation. So you can see one example on the right. So I will briefly present the insight of what we learned looking at those data. So first, it's helped to upgrade the TICFIRE's end-to-end simulator. So I won't go into details into these different blocks, but here I just want to focus on the red, which is the instrument simulator, where we have some optics, about the detector module and processing module. And we use the data at Eureka with the FIR1 to adjust the instrument specification looking at the raw data. So it's really a way to make sure that we are able to reproduce what the instrument have seen using some conditions at the raw level. So it's level 0. And we use level 1B calibrated readances to evaluate radiometric performances. And just one comment. So recently, we also are in the process of adding Saskatchewan as an option for the radiative transfer calculation. Because right now we use Watchman, but we want to have more similarity with Ali and Shaw, so we are going to the second aspect is it's really helped with the algorithm development. So you heard before that for some retrieval, we need some assumption, and especially on cloud structure and microphysical properties, especially the vertical and horizontal heterogeneity has an impact on the quality of the products. So we are using in situ and some instrument on board a conveyor during the wafers campaign. So radar, LiDAR, in situ sensors to evaluate the acceptability of those assumptions. Also, those data sets help to develop the synergy for the synergy of algorithm. So one example is a passive synergy using microwave and IR for cloud properties. And we also want to explore the accuracy improvement when we add the active instrument. And last, for the data processing. So having those data, it really helps to develop the geometric projection to account for aircraft altitude and also for the calibration process. My third point is about we use those data sets to start developing the calibration and validation plan, which is essential to ensure the accuracy of the tip fire radiances and also for the retrieved atmospheric products. So we have identified, showing three of the methods we have considered. First, it's the standalone calibration. So we use simulated and observed radiances, and we compare them to identify some systematic biases. And on the bottom, you see a radiance comparison between pre-fire, Motran, and Sastron. Pre-fire is in red, and you can see Motran and Sastron with where we apply the spectral response function of pre-fire. And you can see in the fine infrared, so after 15 microns, there is quite consistency in this case. So we can use that for tick fire. It will help to better understand the methodology. We use vicarious calibration. So it was a nice presentation by Emily before that shows that having ground sight and for tick fire, especially in a dry location, is very important to assess the absolute calibration and validate the retrieved products. And last, we use some statistical intercomparison with other satellite sensors, and it helps to monitor the long-term consistency. So right now, pre-fire is only 2 CubeSat, and it's supposed to last 1 year. So we are hoping to have some coincident measurements with a forum that will be launched at the end of this decade, because it has a very good high accuracy of 0.25 Kelvin. And at the end, so this database also helps to advance scientific objectives. I've listed 3 of those. The first is radiative closure. So it's an important aspect, and we can compare atmospheric states model and measured at different levels. Having some statistical comparison, characterization of cloud macrophysics and radiative properties, and also looking at the cloud signature in the thermal and fine infrared. And this is an example of the wafers data. So you can see on the colors are for the 8 bands of the FEAR 2 instrument. And you are looking at the cloud relative effects. So it's a cloudy scene minus the clear sky. And we are looking, so as a watt per meter square per steradian, the effect on each band. And you can see on black, it's the aircraft altitude. And you can see we are sampling, the plane is sampling at different levels. So if you are interested, I encourage you to listen to Raphael Peroni's talk next Wednesday. So to conclude, I briefly talk about tick fire with a focus on the thin cloud, microphysics and radiation studies. And also I explained that far infrared observation is kind of new to look at those type of data, and it's really helped to advance the mission science readiness level. So what I've presented today, we have built a far infrared observation database from different sensors at different altitude. It's helped to update the tick fire simulator and do some performance evaluation and improve the algorithm. And also we developed a preliminary calval strategy using diverse methods. The next step, we are going to expand the analysis of wafers using the additional instrument dataset. We are going to prepare for upcoming airborne campaigns, CONNEX, so next January, and ER2 with Ali, Show, and Tick Fire in 2028. We also need to validate the imaging performance for the Tick Fire simulator and Tick Fire instrument. And at the end, we also plan to finalize and release an open version of the Tick Fire end-to-end simulator to the community, because we really want to engage, and I think the simulator is a great tool to work with a different researcher. So that's all from my side. Thank you for listening, and I would be happy to have your comments and questions.
Thanks very much, Jan. Do we have any questions? Are we seeing any online? Any in the room? So, Jan, you're pretty excited for pre-fire. What, if the political situation was different, would you envision that would be something that might be reflown as a constellation, or what do you think?
Yeah, I really think the technology is great. So I see they had some issue with some of the pixels or the wavelengths as well. So it's like a tech demo, and I think it could be really like in a bigger satellite, and it would be interesting to have more capabilities, because right now it's like 15 by 15 kilometers compared to Tick Fire, which is like 2 by 2 or less.
Great.
Thank you.
I'm just looking around. I'm not seeing any other online. Thank you so much, Jan, and thank you for the patience with all the technical issues. Please join me in thanking Jan Blanchard. Very nice talk. Okay. So we're going to hope that we have the online system working. So Atif Tausi is going to be our next speaker. Okay, and Atif, can you try sharing your slides and saying hello? We have an icon, but it's not clear if we have an Atif. Okay. Do we have a speaker that you can see? So are you the one moving this around, or is this our speaker?
So this is his screen.
Okay, great. Great, okay. Let us know when you're ready. No, I don't think so. Okay.
Hi, do you hear me? Do you hear me?
We do hear you. This is great. So at least we can hear you. Can you try sharing your screen, please?
Yeah, I tried to share my screen, but it gave me only what I have in my browser. Okay, I can't share what I have in my desk.
Okay, so why don't we're going to try sharing the screen here, and we'll see whether we can share the screen with your talk.
Screen. Oh, I got it, I think. Oh.
Okay. So let's see. Fingers crossed. Okay, great. So is that you or is that?
Do you see my screen now?
Okay, okay, so you need. So what's up there is. Okay. So can you? Yeah. So can you switch to the other one or?
I'm sharing now
Yep,
my
that's great.
screen. Do you see it or not?
We see it, but we're just trying to get it onto our screen here. That thing down there.
Just stop sharing first.
We're doing it. Yep. So we're good? Okay. So our next speaker is Atif Tausui. Tausui? Tausi, sorry. Telling us about the tick fire simulator. Please take it away, Atif.
Okay, hi, my name is Atif, and I'm with the team, UCAM team. I have, and my subject is testing the tick fire sim satellite instrument simulator during ARM Cape campaign. I will show you the plane. My plane, it's about, we'll show you the context within the HOG framework. It was only done by Jan and Adam. And then I will present the experiment setup. After that, I will follow that by description of instrument simulator model. And after that, I will environmental condition in La Jolla and the result analysis. And after I will finish by summary and for the future work. And for the context, I will not take time for that because Adam and Jan show already that. I will not speak about that and only talk about the experiment setup for the Hawk. Two instruments of the Canadian Hawk mission were flown for instrument test. The tick fire companion was absent for the Hawk ER2 campaign, and it was in December 2023. And the detailed simulator model is used to investigate those three instruments synergy. The first, the simulator validation is done at La Jolla during Cape at the ARM site. That's what will be my experiment. My experience, it will be in the La Jolla to make the simulation with the ER for ER2 campaign. And La Jolla, it was for the Cape campaign, Eastern Pacific Cloud Aerosol Precipitation Experiment. And La Jolla was the main concurrent reference site for HAWK and ER2. The campaign was, the Cape was between December 2022 until February 2024. There were many instruments there: ARI, LiDAR, radar, radiosand, and other many instruments were deployed to monitor local conditions and support the coordinated measurements with Hawk flights. And as you like in the picture, on the bottom. For the fear prototype, I will not take the time because Jan explained more, but only what I will talk about the filters, transmittance, characteristic for band integration. That's what we'll use for the simulation. I will use the some of them with when I will compare with ARI and fear and tick fire, but only between 4 micrometer to 20 to 19 micrometer, and that's why we'll show you why I will use which band and which characteristic integration band I will use. Why my experiment will be to validate or to compare ARI with fear as in the simulator, but I will use ARI even if I don't have fear, because in 2015 and 2016 we compare fear and ARE as instrument, and it was side by side in Eureka, and we got the good results. That's why it will be like it will be like a reference to use the ARE in the place or to replace the fear. And as you like it was on Eureka, that we got the good results. If you see here, the instrument as was described by Jan, and I will use only the two blocks. The first one, the input scene, and the instrument simulator. The technical parameters in the ISM are set to replicate all three instruments, ARI, FAIR2, and TICFire configuration to verification against measurements. And I will use, that's what we'll use here, due to limited knowledge on cloud properties and for more controlled closure conditions, we'll limit comparison to clear sky conditions. For 1D downwelling, and we'll compare the ARE for as measurement and fear and fire as simulation, and we'll talk on the experiment only, and we'll take only the clear sky as a reference. And to verify the condition for in Lajura, we take the UTC and we use the radiscending in 2 PA and 2 UTC. And what, as you see here, that like for the lidar, the sky was clear, and we in the bottom find only ocean haze layer and sea salt aerosol, and like a layer on the bottom of the boundary layer, and but all of the sky was clear in where we make this radiscending. And the same thing with the polarization, it confirm what we get, and in the bottom the same thing, we got the ocean haze layer and sea salt aerosols. To confirm that, we use the Radiscend 2, and we find that's the same thing. We had clear sky. Just after 2 UTC, we got upper clouds. After sounding, we have the formation of the clouds, but after 2 UTC, but in the UTC it was clear. And the same thing in the bottom, we got some haze layer in the bottom, but without cloud. What we get as a result, that's what the result we got for the simulator and compared to ARI. In the left side, the side presents the comparison of downwelling radiances for December 4th at 2 ETC between ARI observations and fire simulation. On the left, we see the spectral comparison without applying fire seam spectral filter response. The agreement between the two data sets is generally strong across the infrared range, with some discrepancies in high absorption region and seen in the residual plot below 2. And on the right, radiance are shown after applying the thick fire seam filter convolution. We have here, if you see at the right side, we have five bands to illustrate the impact of instrumental characteristics on simulated outputs. Difference will remain within acceptable limits, and the consistent pattern reinforces the validity of the simulator under clear sky conditions. This figure support the closure the verification methodology that we are using for both for resolution spectra and band integrated. And after that, I will show in the right side with data here, the figure shows the band integrated validation of thick fire seam radiance output compared to area observation using thick fire filter intervals at 2 o'clock. We are 2 ETC for December 4. Each spectral band T1 until T5 correspond to a physical region to spectrum including HTU vibration rotation until what we have on HTO rotation field. The markers indicate the band averaged radiances from both area with the X mark and thick fire seam with circle mark, while the horizontal lines show the wavelength interval. The small differences between the markers demonstrate good agreement with particularly minimal residual in the 8 and 4 until 14 micrometer window for the window where atmospheric absorption is weakest. It's minimal. These results confirm that the simulator correctly integrates across wide filter bands and capture the primary spectral features seen in the real observations. And the slide presents the band integrated differences between the thick fire seam and area radiances for the same hour expressed by in the left side. We have in the left side we have the difference between simulation and the observation, and the right side we have the percentage for the same thing, but we have the with percentage, and we see for the bands 3 and 4 we have the 4 and 3, almost 4 and 3%, and maybe let's say that simulator accuracy near Pendus is overall the deviation remain within a few percent, confirming that the simulator accurately produces wide band radiance measurement when accounting for the filter characteristics. And this plot shows the correlation between simulated and observed downwheeling radiances, and x-axis represents radiances from thick fire seam simulator, and the y-axis those from area measurements. Each dot corresponds to an individual data point, while large colored circles show the band average value or the mean. We have the line on 1-to-1 dashed line, which represents perfect agreement, the close alignment of most points with this line indicates strong agreement between simulation and observation. The global regression line is like, as you see, is y one, and the square r is 1. Confirm the excellent consistency between the data set. Most band-specific RMSE values are below 0.10, but bands 3 and 4 is like, as you see, 10, the bands 3 and the bands 4 are highly RMSE between 0.10 and 0.12 compared to the others. This increases discrepancies in T3 or band 3 and band 4 may be attributed to the presence of marine haze and sea salt aerosols, which may not be fully accounted for either by the simulator or by ARES. And this suggests that further refinement of aerosol representation could improve closure in these bands for the, we'll check with the area or for the simulator too. And we did the same thing. In this side, we present the band integrated validation results for both stick-fire, SIM, and FEAR. And we applied the same methodology for FEAR and bands as we did for stick-fire. And we now show that both results together. Each curve represents downwheeling radiance for the selected spectral bands, with stick-fire bands labeled to 10 T1 until T5, and FEAR bands labeled F1 to F6. Simulated values are plotted alongside area observations. Overall, the agreement is strong. However, the largest discrepancies appear in the atmospheric window region between 8 to 14, specifically for FEAR. And for FEAR, the F2 has almost shows the percentage for 6%, and TIC-fire T3 that's between shows the 4% difference. And these errors may be from uncertainties in the spectral response or from atmospheric aerosols such as haze or sea salt not fully captured in simulation or in the measurement. For the conclusion, what we see to conclude, we presented a validated TIC-fire SIM simulator using the Clear Sky case from December 4th at 2 UTC over La Jolla. We began with the detailed descriptions of TIC-fire SIM and its instrument modeling chain. Then we focused on the case study during the HAWK campaign, taking advantage of ground-based observation from ARI and radar LiDAR dataset of the EPCAPE site. We compared simulation with observation across both spectral and band integrated levels. The correlation was very good with the global R square R close to 1. TIC-fire successfully, it was the downwheeling radiances seen by ARI. However, some discrepancy were identified. They were most pronounced in the atmospheric window region between 8 to 14 micrometer, particularly for TIC-fire and for the band 3 and for FEAR for the band 2, where percentage differences reached 4 or 6%. For the future work, we aim to extend analysis to cloudy sky condition to test the model's robustness and more, and will extend it for simulation to these spatial domains and retrieval scenarios. Thank you to listen to me, to listen to me. And I finished.
Thanks very much, Atif, for a very nice talk. Do we have some questions in the room? I'm looking around. I'm not seeing anything online. I have one quick one for you, Atif.
Mm-hmm.
You said that your discrepancies were likely with the presence of aerosols. As you work forward in looking at cloudy sky scenes or cases, are you going to need some additional or correlative data to try and tease out what's aerosol, what's fitting, what's more challenging in there?
Yeah, you will. And the simulator will change. Will take the type. We will change the type and try with the marine aerosols. The percentage will. That's why we'll check in the marine for the simulator, and we're for the ARI. We'll check with the team for the and the ARM team to check with them if the ARI is good or not for the aerosol. We'll check for the both of them, for the simulator and for the instrument, and see if there is some what is the cause the problem, or where they miss this simulation.
Great. Thanks very much. Join me in thanking Atif again for his presentation. Okay. I now invite Han back to give her talk. I think you're going to do the share, right?
I use this to change the slides.
Yeah, so that's how you move forward. Okay. And look to see if you need to move the microphone down for you, okay, so we can hear you.
Yeah.
Okay, so our next presenter is Han Huang from McGill University, who's going to tell us about an interesting effect in CAN ESM5 simulations. So please take it away, Han.
Okay. Oh, sorry. Hi, everyone. I'm Han Huang, a postdoc from McGill University. I slightly changed my topic to radar fin effect in CAN ESM5 simulations. And I'd like to acknowledge support from my supervisor, Professor Yi Huang, and also funding from Canadian Space Agency. Okay, so before talking about radar fin effect, let's look at another related topic about the energy imbalance. So this line figure here shows the net radiated flux anomalies from at the top of the atmosphere from the global mean perspective. So by comparing the black lines here, which represent the series observation, and also the rose red line here, which represent the multi-model mean result from CMOS model, we can see that actually the model is doing a not bad job in reproducing the line pattern here. And moreover, in addition to the strong internal variability represented by these two lines here, we can see there is a slightly increase of this net radiated flux as the TOA. And according to one paper by Norman Loeb in 2018, this number is 0.35 watts per meter square per decade. So this means that there is our Earth's climate is gradually gaining energy during this period, and also accompanied with the surface warming. So one related question is, does our climate system has negative feedback mechanism to mitigate such energy imbalance and surface warming? So there has been a long history in trying to identify such negative feedback mechanism. So for example, one is the iris effect proposed by Linden in 2001. They divide the tropical climate into two parts. One is the ascending region, where the atmosphere is moist, so a lot of OLR are attenuated by the atmosphere, and the OLR are mostly originating from the cloud top, so the OLR there is usually weak. And another is the subsidence region, where the atmosphere is clear and dry, so the OLR is much stronger than that in the ascending region. And they propose that such clear and dry region might expand in a warming climate. So this means that there will be more OLR originating from the subsidence region, and thus lead to more energy loss to the space. So this potentially constitute a negative feedback to the climate system. And but there are a lot of debates associated with this iris effect. So unlike their hypothesis, which only focus on the tropical climate, we also conduct a similar analysis of the OR trend for the whole globe. So this figure shows the OR trend from series observations from 2002 to 2019, and the black dots in panel A represent the 95% significance. So unlike the subtropics, where they expect to see a strong OR increase, it is the Arctic region that has the strongest OR increase. And this phenomena is more obvious in the zonal mean perspective, as shown in panel B here. The pink shading represents the uncertainty range of the trend itself, and the black lines represent the region where the trend is significant. So it's so all these two panels here suggest that the Arctic is the region or the only region that had a significant OR increase during this period. And we call this as a radiator fin effect in a warming climate. So to further investigate why the Arctic is distinguished from the other regions, we decompose the total OR trend into several contributions, like the radiated forcing and also the radiated responsive by different components, which can be quantified by the radiative kernel method. And one point I want to emphasize here is that such attribution cannot be completed with only OR observations. And by using kernel decompositions, we can try to find the main drivers of the OR increase in the Arctic. And this figure compares the component contributions to the OR trend in 3 regions. One is the global mean and tropical mean, and also the Arctic region. So the first column here represents the total OR trend in the 3 regions. And we can see that actually for the strong OR increase in the Arctic, it can not only be attributed to the strong contribution. Oh, there is no pointer, sorry. Is there a pointer? Okay.
It's on the screen.
Okay.
They can't see it online.
Okay. Okay, so I will just talk what I'm going to say here. So we can see that the strong OR increase in the Arctic region can not only be attributed to the strong contributions from the surface temperature warming, but also attributed to the strong positive contribution of air temperature warming and also the weak damping effect from the water vapor. So which means that if we look at the last column there, the contribution of the sum of air temperature and the water vapor contribution is much stronger compared with the other 2 regions. So this figures in this way to summarize what the main contributors of the strong OR increase. But one related question is how, but this is from the observation perspective. And one related question is how do GCMs simulate this radiated fin effect, and especially for Canadian models. So before directly showing the radiated fin effect in Canadian models like the CAN-ESM5, we can first look at some properties in terms of climatological perspective. And here show the climatological OLR and surface temperature for the Arctic mean, which means where the area is from the 70 north to the North Pole. And different from the satellite observations for model simulations, for example, for CAN-ESM5, the historical or AMIP simulations, they end in 2014. So here we select another time period. It's from 1979 to 2014. And we can first look at the upper 2 panels, which represent the annual mean time series of the surface temperature and the ORR for the Arctic mean. So quantitatively, we can see there are some differences between the EI5 rain-loss data and also the AMIP or historical simulations from CAN-ESM5. But if we further look at the anomalous time series, which is shown in the lower 2 panels, actually the CAN-ESM5 is doing a good job, I would say, in reproducing the trend or the line patterns compared with EI5. But as I mentioned several times, this is for Arctic mean region. If we further look at the spatial trend in these 2 quantities, we can definitely see some noticeable differences in CAN-ESM simulations. For example, in the Arctic Ocean and also at the locations north to the Europe. And if we further look at other quantities which have interactions with radiation, such as the air temperature, water vapor, and cloud. So actually the CAN-ESM5 model is doing a nice job in reproducing the vertical profiles of these 3 quantities. But if we look at the trend of these 3 variables, we can see some noticeable differences. So for example, in the air temperature, for historical simulations, the air temperature is much higher compared with the other 2 data sets. And for water vapor, both AMIP and historical simulations are simulating a much moist atmosphere compared with EI5. And in terms of the cloud cover change, the EI5 shows a weak cloud reduction But however, for the model simulation, they're showing a slight increase in cloud cover. So all these differences in these geophysical variables will finally lead to the difference in overall trend simulations. And here again, like we are using a similar method as a previous figure. So here, this figure summarizes the the overall trend in the Arctic region from these three data sets. The black box here represents the result from EI5. The horizontal line here, the middle horizontal line, they represent the trend value itself, and the upper and lower two boundaries represent its uncertainty. So we can see that generally the AMIP simulation is underestimating the overall trend in the Arctic region, or in other words, it's underestimating the radar fin effect compared with EI5. And although the overall trend in historical simulation is close to the EI5 result, but actually it's caused by the compensating difference between different physical processes, like the overestimate positive contributions from the air temperature, and also the too strong damping effect from the water vapor and cloud. So in short, I just want to bring this to your attention that the model simulations could show some differences in simulating the OLR or even energy budget trend compared with satellite observations or reanalysis data. And although some model may show some consistent result, but this could be due to the differences in or compensating differences of several different physical processes. So to wrap up, so here is just very brief conclusion. The CAN-ESM5 shows some noticeable, I would say, differences in simulating the dramatic oil increase, especially in AMIP simulations. And also the biases are mostly caused by too much moisture and cloud in model simulations. And that's all my talk. Thank you.
Thank you very much, Han. Very nice talk.
Thank you.
And nice work. Do we have any questions from people? Anything online? So I'm trying to get my head around what I should expect CAN-ESM to agree with. Is this something where part of our work in trying to bring it outside of ECCC is where we can start to make some more adjustments? Do you have like a plan for a next experiment looking at this?
Actually, I mean, here we just like provide some potential causes like the air temperature, water vapor, and cloud. But I think we need to further to talk about those like CAN-ESM5 model developers to see like what are the main controllers in these processes.
Okay. Do you have a plan for what you want to do with that?
Well, to be honest, no, but
not yet.
Not yet, but I mean, I haven't given it a very thorough thought on like what process we are going to do next. But yeah, but I think that's a question deserves a lot of more thinking.
Thanks for the presentation. My question is about the composition in different processes. When we separate air temperature and water vapor, are those two independent, or the air temperature will depend on the increasing water vapor?
Yeah, so physically they are not independent. They actually both dependent on each other. Here in terms of this method, we just linearly decompose into several contributions, or in other words, ignoring the coupling or interactions between these processes. But in terms of like, say, for example, if we want to fix a bias, the difference caused by these different processes, actually they are strongly coupled, I would say.
Thanks very much.
Okay.
Join me in thanking Han again for a great talk. Okay, and batting cleanup today for session 2 of Satellite Earth Observation is Vasura Jawara, who's coming to us from Western University. And do we have a talk? Excellent. Okay. So we're going to hear about a 15-year climatology of free tropospheric relative humidity and temperature. Please take it away.
Thank you. So I'm Vasura. I'm a PhD student at Western University. Today I'm going to present our results from our 15-year climatology in the free troposphere for relative humidity and temperature using Raman LiDAR measurements from Pan, Switzerland. So this is a collaborative project between Western University and the Meteoswiss facility in Pan, Switzerland. So water vapor is the most dominant natural greenhouse gas in our atmosphere, and it can be expressed in several different ways. For our work, we are interested in representing water vapor in terms of relative humidity, because relative humidity is important for many key processes on our planet. So many recent studies have shown that the global surface relative humidity levels have changed significantly over the past few decades. Here in panel A, this is a study done in 2010 by Simmons and others. It shows a clear dominant negative trend across many terrestrial areas since 2000. And also in panel B, it's a study that was done in Canada across 4 different stations, a trend study from 1953 to 2003. Again, we see a negative trend in almost all the stations. So all these results shows that the evolution of the specific humidity has not been able to provide the necessary humidity to keep a constant relative humidity as predicted by the Clausius-Clapeyron equations. So there are 4 main objectives for our research project. So we first started developing an internal calibration method to calibrate temperature and relative humidity so that it will be independent of external reference instruments. So once we had that calibration method, then we started reprocessing and homogenizing 15 years of Raman LiDAR data to obtain temperature and relative humidity. And the 15 years spanned from 2010 to 2024. And then we generated a long-term tropospheric climatology for temperature and relative humidity over Pan, Switzerland. And our last objective, which we are working right now, is to produce long-term trends in temperature and relative humidity in the free troposphere. So for our project, we are using measurements from RALMO, short for Raman LiDAR for meteorological observation, operated by the Federal Office of Meteorology and Climatology in Pan, Switzerland. So the basic process is our system sends a laser pulse at like 355 nanometers, and then the backscattered signal is collected by 4 mirrors. And then the nitrogen and the water vapor signals are separated from the pure rotational Raman signals, and they're inputted into 2 polychromators, the temperature and water vapor polychromator, and then the signal is sent to dedicated photomultiplier tubes and then to the data acquisition cards. So next I'll talk briefly about the calibration technique that we introduced. So Raman LiDAR calibrations can be grouped into like 2 categories, the internal calibration or external calibration. So for external calibrations, we use an external reference instrument such as a radio sound to calibrate. So in our work, we introduce an internal calibration technique which uses solar background radiation to calibrate temperature. So here in equation 1, this is the Raman LiDAR equation, and it has 2 parts. The first part is simply the backscattered signal, and the second part is the background. So here I've used JX to denote either the J high or the J low rotational Raman channel. So for signals that's above, like at high altitudes, like above 45 kilometers, you will see that the backscattered signal is negligible. So we can say that the ratio between the 2 signals will be equal to the ratio of the LiDAR constants times the ratio of the background flux. So extending this, then we can say that the ratio of the LiDAR constant could be tracked by using the ratio of the background and by using some external time T0. So we've used the same calibration method to calibrate relative humidity as well. So if anybody is more interested in learning about our calibration technique, our work was recently published in MT, so you can find more details there. Here I have a comparison between the time series for external and the background calibration technique. So here we used a selected number of dates spanning from 2011 to 2015. So during this time, Meteosys has been launching Vaisala RS92 and RS41 radiosondes to get GRU-1 certified profiles of temperature and relative humidity. So we use these measurements to produce the external calibration time series. The red points are from the RS92 and the blue points are from the RS41. For the background calibration, we used solar background radiation above 55 kilometers, denoted by the black points. So if you compare the two time series, you can see the time series is much more stable after 2013, and also there is they match very well between the two time series. Then we did the validation study. For this, we used a homogenized radiosonde dataset. We used cloud-free nighttime data. And so what we did was we used 175 dates. So we first processed the dates using the background calibration points, and then we calibrated using the external calibration points, and we produced these spaghetti plots. So by comparing the statistics, we can see that they are statistically similar results across most metrics, with the background method exhibiting a reduced variability in some cases, specifically for low altitudes and the mid altitudes. Here we show the nightly, monthly mean temperature climatology from 2010 to 2024 data. On the left-hand side, we have the climatology from our Raman LiDAR, and on the right-hand side, we have the climatology from the radiosondes. Just comparing the two panels, we can see they do produce the expected seasonal variation, where we see high temperatures in the summer months and also much colder temperatures aloft. Table 1 shows the mean bias values between the two temperature climatologies. In the 2 to 10 kilometer range, we get an average mean bias of less than 0.25 Kelvin. And for the low altitudes and the high altitudes, we get average mean bias of less than 1 Kelvin. Next is the nightly, monthly mean relative humidity climatology. Again, it's for data from 2010 to 2024. Again, in the left-hand side, we have the Raman LiDAR climatology, and on the right-hand side, the radiosonde one. If you just compare it for the temperature one, like relative humidity is very chaotic and much more variable, so we don't really see a very gradual, nicer climatology, just like the temperature one. So, but by comparing the two panels, we do see the expected seasonal variation, where we see high relative humidity values near the surface during summer months and much dry conditions aloft. And also we see a very interesting semi-annual cycle in the mid-altitudes, and also in the lower and upper altitudes, we see a more pronounced annual cycle. And comparing again in the table 2, we have the mean biases for the two climatologies. In the 2 to 5 kilometer range, the mean bias is around 1.2%, and in the 5 to 10 kilometer range, we have a high bias of 2.2%. So this high bias could be because the relative humidity measurements from radiosondes could be less reliable in those higher altitudes, mainly due to wetting biases and also the difficulty of measuring very low humidity values that we see at these altitudes. And also radiosondes could drift horizontally from the launch point, and thus they could be looking at a different air mass compared to the LiDAR. So in conclusion, we see that the solar background calibration method helps us to produce a more continuous calibration time series independent of external reference instruments, which helps us to eliminate the drifts associated with instruments such as radiosondes. So this is very important for our work on trends, because our trends would be independent of radiosonde drifts. And by looking at our temperature and relative humidity climatology, we see that both the LIDAR climatology and the radiosonde climatology shows the consistent seasonal temperature and relative humidity patterns that we expect. But in our relative humidity climatology, we also see some interesting semi-annual cycles in the mid altitudes, and also in the lower and the upper altitude, we see some more pronounced annual cycle. As for the next task, we are currently working on producing trends for temperature and relative humidity for the free troposphere. So not a lot of studies have been done for free tropospheric trends. So we believe our trend work specifically on the relative humidity trends would be a valuable addition for the existing literature. So thank you very much. If you have any questions, I'm happy to answer.
Thanks very much, Vishora. Any questions? Sorry, I was going to say, very nice talk. Thank you.
Thank you.
Thanks for the talk. That was great. The nightly, monthly means for water vapor. I'm just wondering what's happening in November. It looks like it peaks at higher altitudes.
Yes. So this is we're seeing some kind of a structure in November. So right now we are not exactly sure what is the reason behind this structure. So November is a very interesting month in Payerne, Switzerland, because they get a lot of fog. And also Payerne lies in the Swiss plateau, so they are sandwiched between like the Jura Mountains and the Alps. And so during November, we get a lot of cold air coming into the valley. So, and there's not a lot of vertical mixing. So we think this could be the reason why we are seeing high relative humidity values, but still we are speculating, so we don't exactly know. So yeah, that could be one of the reasons why we're seeing this. So yeah.
Great, thanks.
Yeah.
Other questions? So how, I was also looking at that and wondering, are there other measurements you could bring in made at Payerne that could help you understand what was happening in that? Or is it really, you know, you've got the sondes, you've got the Ralmo, and that's about
yeah,
it?
that's kind of, yeah, radiosondes would be the other option. So right now we are doing another research at Météo Suisse is doing another long-term trend study and climatology using like a much larger data set. So that would be interesting to see whether how it would compare to this one. So yeah.
Great. Well, please join me in thanking Vishora again for a very nice talk.
Thank you.
And thank you very much to everyone online and everyone in the room for withstanding yet another set of wonderful technological challenges and to be able to see the great science that we have going on. Please go grab some snacks. We will start again as close to on time as possible. Thank you.